This is an ordinary chicken egg. If I pick it up and drop it a few inches, not much happens. It kind of hits the ground and stops. But let's carry it up to a greater height. So Kyle is walking up steps. He's going to hold the egg up, and so now it's 15 feet off the ground. And look at the egg now. Now what's the difference? It hit the same ground and it's the same egg, but that definitely is not the same change. So let's talk about that. What did the egg have at, say, 4 or 5 meters high that it did not have while it was on the ground? So I take it, or my son takes the egg up high and drops it, and there's a difference than if you just drop it a couple of inches. It's the same egg, it's the same ground, but the egg has something that it didn't have before, and it causes a different sort of a action, you might say, when it's carried up high. Now, your first response is probably, yeah, so what? I mean, everybody knows if you drop an egg from a height, it's going to break. But have you ever really thought about that? It's the same egg and it's the same ground. So why does it break in one case and not in the other case? Okay. That really is kind of an interesting question if you give it some thought. But people say, oh, no, that's an easy answer. And the answer is gravity. Well, my question to you would be, well, what's gravity? But even more than that, gravity doesn't really change just because you go up 15 feet. I mean, there will be no measurable change in gravity at that height. So it's not gravity per se. So you might say, well, it's the height. That's what caused it. But height is a measurement. It's just an indication of position. It's not a quantity a property that, the egg actually possesses. So that's not exactly what we're looking at either. It's definitely related something to gravity and it's related something to height, but it's not really either one of those measurements. Something else. Clearly, the egg, when it's carried up the stairs, acquires some sort of property that it did not have while it was near the ground, or at least it acquired more of this property when it was lifted up than it had when it was close to the grass. So this ability to create an action, a fall, and then a breaking is known as energy. And that's our topic for today. And in particular, we're going to look at this energy that comes from gravity, from height. Okay. But in a more broad sense, energy is an ancient concept. The idea of energy has changed over time, but even Aristotle used a word very similar to what we use today that meant basically activity. So energy causes activity. So energy makes things happen. If the egg is being held up high, it somehow had energy inside it. That energy was stored up somehow. But when the egg was released, it fell. And not only did it fall, but it moved faster and faster. If we could look at the speed of that egg, we'd see it was speeding up, speeding up, speeding up until it got to the ground. And when it got to the ground, what happened then? What happened to the energy that it had that we said it somehow acquired by going up the stairs? Did that energy just disappear from the universe? Was it used up somehow? Well, if you could see the video on your own computer somewhere, you might have noticed several things. It did stop falling, but it didn't stop changing. It cracked open. There was a mess that spread out over the grass and over the leaves. It moved the leaves, it moved the grass, and it even made a sound. It went splat. So a sound was created and moved away from the point of impact. All those changes occurred because this energy caused them. So somehow the egg acquired energy, and then it released that energy and caused changes in its own surroundings. So where did that egg get the ability to cause this motion and change in the first place? Well, it came from Kyle, right? From Kyle picking it up. But where did Kyle get the energy? Well, we could go on and on with this. The point is that whatever this energy is, it can move. It can go from one place to another, from one object to another. So it's something that an object can have, and it's something that an object can acquire, and it's something an object can give away. And whatever this property is, it can cause change, it can cause actions. So what is energy? Well, I wish I had a good answer for you, but I'm not sure anybody could really give you a good answer for what energy is. It's just part of the universe. It is what it is. Okay? It's one of the most fundamental things. Usually whenever you define something, you break it down into, finer parts. So you can't do that with energy. It's the most basic thing there is. So whatever it is what it is. Instead, the way energy is typically defined is not what it is, but what it can do. Okay, so we said that it can cause change, it can make actions and activity. So, sort of a very simplified definition that you often run into is that energy is the ability or the capability or the capacity. Sometimes people use different words there, but I like to use this term. It's the ability to do work. Okay. And we mean that work in the physics sense. In other words, a net force causes a motion. Now, this definition, the ability to do work, is not a great definition. It would be much better to say that energy is some kind of property that must be given to an object or a system in order to do work. And what we often ignore with our simplified definition is that there's also a sort of a related part to the work, and that's heat. In almost every situation that we've ever run into, if any work is done, heat is also transferred or released, okay, or absorbed. So a better definition might be to say that work is a property that must be given to a system in order to do work or to heat it, and it's a property that the system loses when it does work or loses heat. So like when the egg gave something to its surroundings. All right. Now that's a pretty complicated definition. And so we're going to just stick with the earlier definition. But I just wanted to keep that in mind, that the ability to do work is not really the whole story. So if energy is the ability to do work, energy and work are not the same thing, but they're definitely related to each other. In fact, work in the physics sense means that a net force causes a movement or a change, maybe a change in shape, for example. Well, a force in turn there's only a net force if there is an acceleration. Force equals mass times acceleration. Okay. So what acceleration is any change in speed or direction. Or again, you could include a change in shape there. The point is that if you go through the logic, if energy is related to work and work is related to force and force is related to a change in speed or direction, then you could say that energy is responsible for all motion, or at least all changes in motion. If motion is constant, then no energy really is involved, but any change in motion must be related to energy. So that's kind of an interesting way to look at it, that energy is some kind of fundamental property of the universe that causes changes. And in our particular case, we're most interested in changes in motion. So when the egg was being held in Kyle's hand at a height, if he had paused, let's say, for a couple of seconds, it really wasn't changing anything. It wasn't accelerating. And so in that sense, the energy must have been stored up inside the egg somehow. But then when he opened his hand and the egg fell, the energy was doing something. So in a very broad sense, there's sort of three categories, if you will, of energy that we need to look at. There is the case of when it's being stored up, held inside somehow. There's a case of when it is causing a change, moving something. And then there's that aspect of heat, when energy comes or goes and causes a temperature change. We call that heat. It doesn't really move anything other than a few atoms or electrons around. And it's not really being stored. It's not doing any useful work, we say. We call that heat. So that's our three categories of energy. Whatever this energy is, we're going to look at three categories: when it's being stored up, when it's causing motion, and when it causes temperature changes. So here's an example of when energy might be stored up. If you've ever shot a bow, for example, you pull back on the string, and then when you release, somehow the string moves, the string pushes the arrow, and the arrow moves, and the arrow goes down, hopefully, and hits the target. But the point is that right before you shoot the arrow, you're just holding the bow. That energy is stored up in there somehow. All right. Here's another example. If you go and to Kentucky Kingdom or somewhere like that, and you get on a roller coaster, a chain will pull you up to the top of the first hill. Well, it's storing up energy. It's like Kyle walking up the steps with the egg in his hand. Here, where a chain is pulling up a whole cartload of people to the top of the hill. And then when it lets go, somehow the cart has the ability to move around the track. So that energy was stored up in there somehow. Here's another case of energy being stored up. We put fuel in our vehicle, like gasoline going in a car, and somehow you set a spark to it, it releases energy that's been stored up inside. The point of these three examples is that they're all examples of energy being stored up, but it's stored up in different ways. Okay, in the case of a bow, it's stored up because of the position of atoms. Some are squeezed close together and others are stretched far apart. In the case of the roller coaster, it has to do with the position of the coaster with respect to the ground. It's some sort of position of gravity effect. Okay. And in the case of gasoline, it's actually a movement of electrons, the position of the electrons and how they change position, that somehow releases energy. In each case, it's really related to position, but there are differences. Now, what a lot of teachers do at this point is they start going into all these different categories and giving them different names. I don't really like to do that. They're all examples of stored energy, which we just call potential energy. If the energy has the potential to do work, then we're going to call it potential energy, regardless of where it comes from, whether it comes from the position of molecules, the position above the ground, the position, the arrangement of electrons, or even nuclear particles. If you're talking about nuclear energy, there's lots of different types, you might say, of potential energy. But you know what? Every single one of them is actually the same thing. They're all energy. It's all a property that's somehow put into an object or a system that now has the ability to do work if conditions change, like if you open your hand. Okay. So we can give them all different terms like elastic potential energy and gravitational potential energy and chemical potential energy. I just think that's trivial. I don't think that's really important. Okay. What's important is that you understand energy is energy. It is whatever it is, the ability to cause action. But it doesn't always cause action because it can be stored up. And anytime it's being stored, that's potential energy. Having said all that, though, this is physics class. And in physics class, whoops, was I forgot that was in there. I'll let you read that. So anyway, that's just a joke in case you were paying attention to the slides earlier. I was putting egg puns on every slide. This is high school physics, and then we are expected to do some word problems, some calculations. So I do want to do some calculations involving potential energy, but we're just going to use gravitational potential energy and use the gravitational potential energy formula. So we could put GPE, gravitational potential energy, but I'm just going to call it PE. But just be aware that there are different sorts of formulas depending on which of these potential energies you're calculating, but they're all going to give you results in energy units. So let's talk about that. What is an energy unit? Well, in our last lesson, we learned about the physics concept of work, a force being applied over a distance, such as lifting a box. Okay. We said, for those of you that were paying attention, that if you're lifting something, the force that's involved is the weight of the object. And the weight is its mass times the acceleration due to gravity. Now, here on the Earth's surface, the acceleration due to gravity is 9.8 meters per second squared. But for our purposes, just to make our calculations a little easier, we were using 10 meters per second squared. Okay. We were rounding off. I noticed one or two people on the answers to the worksheet yesterday that used 9.8. They obviously went to some website or some person and got the answers. You really should read the question and what Dr. Kemp has to say. We are rounding off to 10. Okay. So lifting this box, the work would be mass of the box times acceleration due to gravity. That's its weight. Mass times gravity is weight times how high do we lift it. That's the distance through which it's displaced. All right. What's the point? Well, the point is it doesn't matter whether it's a box or an egg or a roller coaster. That formula will give us the work value. And we said earlier that energy is the ability to do work. So energy somehow got to be related to this formula, right? Work and energy are not the same thing, but basically, if energy is being used, work is being done. So if work is being done on a system, then energy is being transferred into it. So if you're picking up a box, you must be putting energy into it. If you're putting down the box, then energy must be coming out of it. It's losing or transferring energy to its surroundings. So we could mathematically, tentatively say something like this, that if work and energy are related, any change in energy must equal the amount of work being done, or at least it approximates it somehow. It's related to it. Or we could, instead of putting delta energy, we could put delta work. We could say energy equals any change in work. So the work that's done at the end minus the work that was being done at the beginning. So one of those two formulas ought to really help us out. If the amount of work to lift a box or an egg or a barbell or whatever is mass times gravity times height, and if we said work is a change in energy, then we could just substitute that delta E, the change in energy, for the W. In other words, we now have a formula for energy, at least the potential due to gravity, due to height changes. Okay. So if the potential energy, or delta E in this case, or like I said, we could call it PE, or we could call it GPE, or you can have whatever symbol you want. I'll just probably use PE most of the time, meaning potential energy. It must equal mass times gravity times height. Okay? That's our formula. potential energy equals mass times gravity times height. You can leave the dots in or you can take the dots out. Any letters beside themselves means multiply. Now, I do want to make sure you understand, because again, this was missed by a couple people on a worksheet problem from yesterday, that the height refers to a difference in position. So it may be sitting still at some height, but what you have to do is measure it relative to the ground or relative to the floor or relative to something. So height in this formula always refers to a comparison of where something is and something else. All right. So usually we will choose the ground or the floor as height equals 0. The mass and the acceleration due to gravity multiplied by each other give a weight. So if the problem gives you a weight, then all you need is weight times height. If it gives you a mass, you got to multiply by 10 meters per second squared. Okay. So here's a question just to see, here's an example. Make sure you understand. This boulder is sitting on the ground. It weighs 100 newtons. It's picked up and set on this little ledge 2 meters high. Okay. It now has a potential energy of weight times height. 100 newtons times 2 meters is 200 newton meters. And a newton meter is the same as a joule. So in the diagram, you'll see it's written 200 joules. Now, this is really important. We picked the boulder straight up, but what if we pushed it up a ramp? Well, we may push it up, a really long ramp, like 4 meters long. But if in the end it is 2 meters high, it's got the same amount of potential energy as it had before. Potential energy is what we call a state function. What that means is only the beginning state and the end state matters. It doesn't matter how you get from one place to the other. It only matters what was the beginning, what was the end. So if you pick it up, if you push it up a ramp, or even if you just carried it upstairs, it's going to have the same amount of potential energy because its final position is 2 meters above its initial position. Okay? It's the same mass, it's the same weight, same gravity, and the same height difference. It doesn't matter how it got there. So, just a little summary of what we've said so far. This gravitational potential energy, which is the only type we're focusing on today in our worksheet, is equivalent to the work required to lift something. And the work required to lift something is mass times gravity times height, or weight times height. If you're given kilograms, you use mgh. If you're given newtons, you use wh. Okay? Did you write that down or make a mental note of what I just said? Because it's really important. If you're given kilograms, that's a mass. You got to use the first formula, mgh. If you're given newtons, that's a weight. It's mass times gravity. Gravity's already in it. So if you're given newtons, use wh. But the h is the difference between where the object is and some reference point. Usually, that reference point will be the ground. Not always. You got to read the question very carefully. Okay. So if potential energy equals work, and work is measured in joules, guess what potential energy is measured in? Joules, Newton meters. Okay. If you measure weight, that's newtons, and height in meters, and multiply them by each other, that's going to be Newton meters. Point is that joules is the unit of measurement for energy as well as the unit for work. So here's a little question series to see if you can relate today's lesson and the last lesson on work. You lift a 100 Newton boulder 1 meter high. How much work is done on the boulder? What power is expended if you lift the boulder in a time of 2 seconds? What is the gravitational potential energy of the boulder in its lifted position? Work was mass times gravity times height, but we're not given mass, we're given weight. So we'll just use weight times height. So work would be 100 Newton meters. All right. A Newton meter is the same as a joule. Power is work divided by time when you have time in seconds. So it's 100 joules divided by 2 seconds. That's 50 joule seconds, which is the same thing as a watt. So 50 watts. What's the gravitational potential energy? Well, it's the same as the work. So if it is 100 joules of work, then its potential energy is 100 joules. Since we picked it up, it's a positive. If we were putting it down on the ground, we might list that as a negative, just meaning that the boulder lost energy. But it doesn't ask us that. Okay, relative to the starting position, the height difference is 1 meter. So it's 100 newtons times 1 meter, which equals 100 joules. Our next topic will be the other next category of energy, what happens when things move. But this topic is just what happens if they're lifted and the energy is stored up.